When you want to travel a long distance, say from one continent to another, you book an airplane flight expecting to spend some hours in the air. However, when it comes to space travel, you need to travel faster because all the points of interest are so far away. Space explorers have always been searching for a way to travel faster than light, which will allow them to get to deep space more quickly. Basically, all the methods discovered have significant drawbacks, but scientists have found a new way. How does it work? What are the requirements? How soon will you be able to travel with it? Join us as we bring you a new way to travel faster than light. Light is fascinating and very important because without it, it would be difficult to watch this video. Thanks to the sun and other artificial light sources that humans have come up with, we can walk without running into objects unexpectedly. However, you have probably heard light travels and travels fast, but how fast is light? Interestingly, the exact speed of light is known and is the basis for most other measurements. The speed of light traveling through a vacuum is exactly 299,792,458 meters, or 983,571,056 feet per second. That means light will travel about 186,282 miles in just 1 second. Light is so fast that if you switch on a bulb in a dark room, the light fills everywhere nearly instantly and you won't notice that light travels. Another unit of measurement involving light is the light year, which is the distance that light can travel in 1 year. This value is about 6 trillion miles or 10 trillion kilometers. It is one way that astronomers and physicists measure immense distances across our universe. As mentioned earlier, the universe is so vast that it can take light many years to travel from one part to another. To illustrate, light travels from the moon to our eyes in about 1 second, which means the moon is about 1 light second away. However, sunlight takes longer, requiring about 8 minutes to reach our eyes, meaning the sun is about 8 light minutes away. Light from Alpha Centauri, the nearest star system to our own, requires roughly 4.3 years to get here, so Alpha Centauri is 4.3 light years away. Other stars and objects beyond our solar system lie anywhere from a few light years to a few billion light years out. This is why everything astronomers see in the distant universe is literally history. When they study objects that are far away, they are seeing light that shows the object as they existed at the time that light left them. While there are a lot of fascinating things you can do with light, scientists have tried to find a way to travel at the speed of light. This is interesting as humans will finally become an interplanetary species. For instance, SpaceX billionaire CEO Elon Musk wants to form a settlement on Mars, but his explorers have to bear at the minimum 5 months of travel through space before touching down on the red planet. This can even reach almost a year depending on how close the two planets are, and that is with all the hazards it brings before touching down on the red planet. However, with speed of light travel, they can make a long trip in less than 4 minutes. Researchers have tried many different methods to achieve traveling at a very high speed. However, until a scientist announced the new discovery we will bring you in this video, there has always been a problem that all other methods could not solve. Even to achieve 1% of the speed of light, which is still plenty fast as it can take you from Los Angeles to New York in a little over a second, is very hard. The problem, in a single word, is energy. Any object moving has energy due to its motion, and physicists call this kinetic energy. To go faster, you need to increase kinetic energy. The problem is that it takes a lot of kinetic energy to increase speed. To make something go twice as fast takes 4 times the energy. Making something go 3 times as fast requires 9 times the energy, and so on. For example, to get a teenager who weighs 110 pounds to 1% of the speed of light would cost 200 trillion joules. That's roughly the same amount of energy that 2 million people in the US use in a day. Take, for example, the EM drive, which was touted as the technology that would take us to the most distant parts of the universe very fast. This invention, which has even been patented, theoretically works by trapping microwaves in a shaped chamber where their bouncing produces thrust. The chamber is closed, meaning from the outside it will appear to simply move without any fuel input or any thrust output. The EM drive relies on Newton's second law, where force is defined as the rate of change of momentum. Thus, an electromagnetic or EM wave traveling at the speed of light has a certain momentum that will transfer to a reflector, resulting in a tiny force. This accumulated tiny force in great quantity is what enables the EM drive, which sounds simple but also essentially turns our understanding of physics on its head. No energy is going in or coming out, which makes us ask questions like, how are the waves initialized? How do they continue to move? And where is their momentum coming from? You can't have spontaneous created momentum without an explicable push, which is why many scientists don't even take the EM drive seriously. If the EM drive works, then it invalidates much of what physicists know about the universe. The EM drive was even put to the test by physicists at the Dresden University of Technology that showed that the promising results obtained by NASA and China showing thrust were all false positives explained by outside forces. However, the warp drive shows great promises, as shown by Dr. Eric Lentz, a physicist with over 10 years of experience in practical applications. Lentz wasn't even the first to work on making the warp drive a reality and not just sci-fi. The first person to attempt it was the Mexican mathematician Miguel Alcubierre. In 1994, his proposal became the beginning of the official literature on warp drives. Unfortunately, the Alcubierre warp drive, as it has come to be known, requires a staggering amount of energy, along with the dreaded exotic matter as a co-ingredient. This highly radioactive stuff is only theoretical and is not something researchers have actually observed in nature, much less created. A handful of variations have been suggested since, including a 2010 update to the Alcubierre drive's physical design made by former NASA engineer Dr. Harold G. Sonny White. His update reduced the amount of energy needed to a less daunting number, even though it was still not practical because the solution also still required exotic matter, albeit significantly less than the Alcubierre solution. Another group of researchers from Switzerland known as Applied Physics APL put forth their own concept. Interestingly, their drive did not need any exotic material to create its warp bubble. However, their model could not go beyond the speed of light, which is the holy grail of space travel. To explain how his concept is different from those already proposed, Lentz first points to the physical structure of the classical Alcubierre drive, on which nearly all other solutions are more or less based. He said the Alcubierre solution provided an intuitive picture of what a warp drive would do, that is, contract the space immediately in front of the central region containing the ship or transport and expand the space immediately behind. This shows the warp drive as a wave of curvature on which a ship will ride to its destination. Even though it is the cornerstone of warp travel, Lentz argues it is not even the essential feature. Instead, he says a solution proposed by physicist Jose Notario back in 2002 showed that the expansion and contraction weren't necessary to transport the ship forward. That work prompted him to rethink how a warp could be created using only traditional matter and not exotic matter. Notario was able to prove that the expansion could be trivial or zero everywhere and still perform the same task of transporting a ship. This is a significant breakthrough because it means that exotic matter that warps the space in front of the theoretical passenger and behind them in nearly all theoretical warp drive solutions is no longer needed. And by building on Notario's theory, Lentz created his own variation that he believes is even more viable because it is rooted in conventional physics. Aside from this key material difference, Lentz indicated that his solution differs from Alcubierre and most others geometrically due to how the energy is placed around the warp bubble. In the Alcubierre solution, the energy density and curvatures are maximally separated, with the energy being restricted to a small torus between the regions of high contraction and expansion. The curvatures and sources in Lentz's proposal are instead highly correlated, with the regions of high energy density and high expansion and contraction overlapping almost exactly. It is these geometric distinctions between his concept and the traditional concepts that make Lentz's proposal a potentially more viable warp solution than those previously proposed. Of course, Lentz's warp drive is still completely theoretical. He does, however, see a few steps that can be taken right away to try to move his version closer to reality, which, like all previous drive theories, includes reducing the amount of energy needed. Where does Lentz want to take his warp drive from here? He said the next target is to make a warp bubble capable of moving at 1% the speed of light using a modern-day fission reactor. The physicist said he would consider patenting his warp drive, but he made it clear his work is just part of a larger, rapidly growing body of work in this area, and that the recent increase in warp drive concepts since Alcubierre's 1994 proposal gives those in his field hope that a real, testable version may be closer than we think. Len said it has been exciting to see how much progress has recently been made in the field of warp drive. He thinks many more advances are ready to be made and looks forward to seeing what the next few years bring. Let's hear what you think of speed of light travel in the comments section below.